the atrial and ventricular pressure. So we're going to speak about the cardiac cycle events from a different perspective this time, looking at what's happening in the atria and the ventricles more specifically. So phase one, this is our diastole, the beginning, the latter phase of our diastole. And this is where the atrial pressure rises slowly as filling takes place from the atria down into the ventricle. The ventricular pressure is low. It must be low in order for that valve to be open. Remember, atrial pressure must exceed ventricular pressure for AV valves to be open. There is a small rise in the ventricular pressure at the end due to that atrial contraction squeezing that last bit of blood out at the end of phase one. So here's the start of our atrial contraction. Notice that it's the halfway point of phase one, where the atria and the ventricles have a slight increase in their pressure. If we think about phase two, this is a rapid rise in ventricular pressure. Notice none of the valves are open here. This is a very short transient period to get the ventricular pressure high enough to exceed the aortic pressure and to lead us into phase three. All right, so here we can see that pressure steeply rising. In phase three, ventricular pressure falls, right? Notice that we have an increase initially, but then it drops off as blood moves out of that ventricle. So initially it's high, but then it drops off as blood leaves that chamber. Atrial pressure stays consistent and dips a little bit as the atria are relaxing in this period. And then, ventricular pressure is going to drop off in phase four. So phase four here will be isovolumetric ventricular relaxation. Our valves are closed in this period. Pressure's dropping off in order for the AV valves to open once again, and that'll bring us right back to phase one. Let's look at this in a different way. So let's talk about the two general phases of the cardiac cycle, diastole versus systole. So what is corresponding to diastole? Diastole is the filling of the heart. So it would make sense for diastole to correspond with phase four and phase one, right? Phase four, phase one would be representative of diastole. Our semilunar valves are closed, okay? Blood is leaving the aorta, so the pressure is gonna fall off. Okay, if we think about our blood leaving and the atrial pressure dropping off here, or the aortic pressure, dropping off here. And in the lowest point of diastole, we can measure our diastolic pressure. So the lowest aortic pressure that is recorded during diastole, again, phase four, phase one, the lowest aortic pressure, we can mark that as our diastolic pressure. The highest pressure that's recorded, which is in systole, that's going to be recorded as our systolic pressure. And we'll talk about how these two numbers are extremely important for overall cardiovascular health. This is what constitutes our blood pressure readings. All right, but the first one we record in diastole. Let's talk about systole. So systole now is going to correspond with phase two and phase three. The isovolumetric contraction of the ventricles followed by the ventricular ejection. So our aortic valves are going to be open at this point, which makes perfect sense since the ventricles are ejecting. Pressure is going to rise rapidly initially and then fall off as that blood moves away from the chamber. The highest point that we measure during systole, right? So if you think about phase two to phase three, our highest aortic reading is referred to as our systolic pressure. Okay. At the end of that, we're going to have closing of the aortic valves, and then we're going to move into phase four, which is where we're going to lead into diastole. Now, the backflow of blood against the closing aortic valve is what we refer to as that dichrotic notch. So we have blood leaving the ventricle here, moving out into the aorta, or if you want to think about it, the pulmonary artery, but this is specific to the aorta. And then as the blood from that high resistance systemic circulation hits against the back of the closing semilunar valves just before phase 4, we see that dichotic notch, which is a reflection of the pressure of that blood hitting against the closing valve. Okay, but the important point that I want to capture here is the systolic reading, the highest aortic reading in systole versus our diastolic pressure, the lowest aortic reading during diastole. And these two numbers constitutes blood pressure. So our average blood pressure reading will look like 110/70 or something more close to 120/80 in our typical physiologic state. All right. Let's talk about the aortic pressure here. And on that basis, we can think about the mean arterial pressure. This is the average aortic pressure across the entire cardiac cycle. So if we look at the change in this pressure, so here we have our pressure curve, right? We're starting at about 80. We're dropping down to 70. We're going all the way up to 110. And then we come all the way back down to 70, right? If we take an average of all those pressures through the entire cardiac cycle, that gives us our mean arterial pressure, or our MAP. And what this number tells us is the driving force with which blood is moving throughout our systemic circulation. All right, so because the pressure can be high at some points and low at some points, we're going to average that out and tell us what is the overall driving push of that blood leaving our ventricle, moving into the aorta, and then subsequently into our peripheral circulation. What is the average force with which blood is leaving the heart? That's our mean arterial pressure. It's going to be a continuous blood flow through the entire cardiac cycle. And then if we look specifically at the aorta, which is our large elastic artery, the aorta is going to act as a pressure reservoir so that the pressure is never really dropping to zero. We can capture some of that pressure in the elastic walls of our aorta. And so that's going to help maintain the average driving force, or the circulatory force with which blood is leaving our ventricle. Okay, so we can store some of that energy, that recoil energy, in the elastic walls of the aorta, and then we can release that energy the same way you would releasing an elastic band, and then that recoil will help to push or propel the blood forward and maintain that driving force throughout the entire cardiac cycle. So the aorta is one way that we can maintain continuous pressure throughout all periods of the cardiac cycle, even when the valve is closed, for example. When the valve is closed, we would be tempted to think that the pressure would drop to zero, and that doesn't happen because of the elastic nature of the aorta. All right, let's illustrate that here. So here's our aorta in systole. Here's the flow of blood coming from the left ventricle. Here is our aortic valve. And as we can see, during systole, there's no problem maintaining flow or maintaining pressure because we have that active contraction coming from the left ventricle. So blood can move freely out from the aorta out into our systemic arteries and organs. Notice, however, that as we expand the aorta, because it's such an elastic vessel, it's going to capture some of that pressure in the wall of the aorta itself. If we think about how this changes for diastole. So remember, in diastole, what's happening? Our ventricle is filling. So now the AV valves are going to be open, and the semilunar valve, including our aortic valve here, will be closed. So we would be tempted to think that since the aortic valve is closed, the pressure in this artery will drop to zero, and that doesn't happen. What happens instead is the elastic recoil, the pressure that has been captured in the wall of this aorta, will then sort of forcefully propel the blood in this artery out into the systemic organs. And so even during diastole, we can maintain good perfusion. We can maintain good flow from our major arteries out to our systemic organs, even when the aortic valve is closed. Okay, so that elastic nature of the aorta is extremely important to keeping our systemic circulation adequately perfused. All right, let's look at our volumes. So we've talked about our pressure, especially the pressure in that aorta. Let's talk about our volumes in the ventricles. And this is going to help us understand how much is the chamber filling, how much is the chamber ejecting. So the first one is the end diastolic volume. And these names tell us exactly when we record these volumes, right? At the end of diastole, after the chamber, the ventricle that is, has filled, we're going to go in and we're going to read that volume. How much has the ventricle filled at its highest point, its ultimate point of filling? Then we can think about the end systolic volume. At the end of systole, after the chamber has fully and completely ejected, how much blood is left back in the ventricle at the end of that ejection? All right, that's going to be our end systolic volume. And if we think about it, we can record our end diastolic volume. I'm going to go back here just to illustrate this. We can record our end diastolic volume at the end of diastole. So that is anywhere along phase one, right? At the end of phase one, we're going to have the maximum amount of blood that can be filled in the ventricle filled, and then the AV valves close. If we think about the end systolic volume, that we can capture at the end of phase three. So this is after the ventricle has ejected. Remember, phase three is ventricular ejection. So after that ejection, then we're going to go in and check the lowest volume, and that would be our ESV. So our end systolic at the end of phase three, our end diastolic at the end of phase one. Okay. And then the other two volumes here are derived from those two initial volumes. So the stroke volume, that will tell us how much blood has been ejected. And if we take the amount that was filled and we subtract the amount that's left behind, that will be a way that we can calculate how much has actually left the ventricle and moved out into the artery. So in order to calculate our stroke volume, we take our end diastolic volume, around about 130 mLs. We subtract our end systolic volume, what was left behind, around about 60 mLs. And so about 70 mLs has been ejected from the ventricle. On that basis, we can further derive our ejection fraction. So the ejection fraction is a ratio. It is the end diastolic volume ejected during a single heartbeat. So it is how much of your filling volume did you eject? How much of the entire amount that you filled into that ventricle did you end up ejecting versus how much was left behind? So that is our ejection fraction. So we want to take our stroke volume and we want to divide it by our end diastolic volume. And so if we take 70 milliliters, how much was ejected? And we divide that by 130 milliliters, how much was filled to begin with, that gives us a ratio or a fraction of about 0.54, which is 54% at rest. And what this number tells us is 54% of our total filling volume was ejected at rest. Of course, if you're exercising, if you're an athlete during performance, that number is going to go up. You're going to eject much more, of your total filling volume. This number is just representative to someone at rest. All right. I just want to illustrate how we can connect the cardiac cycle events to what's happening with the volumes. So notice we start off, this is phase one. We are filling the ventricle here. So we start off with some blood in our ventricle, but then we fill to our maximum capacity of 130 milliliters. So at the end of phase one, we can record our end diastolic volume. We eject blood during phase 3, and so our volume will steeply drop off. Therefore, at the end of phase 3, we can record our end systolic volume. And then we can take those two numbers and subtract 60 from 130, and that will give us our stroke volume, which is 70 milliliters ejected. All right. As far as the pressure volume curves, these help to tell us how both pressure and volume are related during the cardiac cycle. And these can also tell us about any states of disease of the heart. If there's a stiffened ventricle, we can determine that from the pressure volume curves. If there is a leaky valve, right? If you have a calcified valve, a stenotic valve, or a regurgitating valve, a leaky valve, we can tell that from changes in the pressure volume curve. So phase 1 we can see here is ventricular volume increasing. This is the filling of our ventricle. Notice that we have the volume increasing and then the pressure increasing as well. Phase 2 is where we have isovolumetric. So in phase 2 and phase 4, we would not expect our volumes to change. Therefore, we can expect a straight vertical line in both phase 2 and phase 4 as volume stays the same, but pressure rises for phase 2, isovolumetric contraction, okay, but volume stays same. And then in phase 3, we have ejection. And as you would expect, volume must decrease if we are ejecting blood. So our curve moves backwards, right? Because we're going from 130 to 60. So this is what gives us the loop in our curve. This is going backward. And then phase 4, pressure falls, volume stays the same, right? Isovolumetric ventricular relaxation. Our vertical line again, because the volume doesn't change for phase 4, but the pressure decreases sharply, and then we go back down and start our phase again, our cycle again. Okay. The last bit to squeeze in here is the heart sound. So the heart sounds are basically made due to the turbulence of blood flow against a closing valve. The first heart sound is a soft lump, right? That is the closure of the AV valves, specifically the back shift of blood against those closing valves. So it's not the valve itself that's making that sound. It's not the blood that's swooshing alone to make that sound. It's a very specific phenomenon of the blood hitting against the back of the closing valve that results in that soft lump or the AV valve closure. The second heart sound is a louder dup, right? So it's lup dup, lup dup. It's a slightly higher pitch. And this one is due to the semilunar valves closing, which will happen at the end of phase 3 here, at the end of ventricular ejection. Our semilunar valves close. And as blood hits against the back of that semilunar valve, then we have a louder dup. There's more peripheral resistance in the systemic circulation, and so that's going to be a louder, more high-pitched sound against the back of semilunar valves than it is against the back of AV valves. So it's a lup dup, and that would be AV valves followed by semilunar valves. Right.